when you picture building a liquid rocket engine, your brain probably goes straight to the fire. Like you think of the thrust and the flames.
Right, the actual ignition.
Exactly. You think the hardest part of the engineering is just getting these massive amounts of fuel and oxidizer to mix, ignite, and, push a vehicle upward.
Yeah, which makes sense.
But you might be surprised to learn that ignition is, well, it's actually kind of the easy part.
It really is.
The real nightmare, like the absolute hardest part of rocket science, is keeping that engine from shaking itself apart.
Yeah.
Or, melting into a puddle of slag in less than a single second.
Yeah, it's a razor-thin line. I mean, you're balancing between a controlled, continuous explosion that takes you to orbit and a violently uncontrolled oscillation that just tears millions of dollars of aerospace hardware to shreds.
And that brings us to the mission for this deep dive. Today, we are exploring this highly technical engineering document on the principles of liquid rocket engines.
Specifically, we're looking at Chapter 5.
Right. Zeroing in on this terrifying phenomenon known as combustion instability. So our goal for you today is to totally demystify this critical hurdle.
We're going to decode the physics of why rockets vibrate so violently.
Yeah, and how engineers physically tame those forces, plus the, frankly, wild lengths they go to test them. Okay, let's unpack this.
Sounds good.
To understand why an engine would just suddenly decide to rip itself apart, we have to look at the baseline environment inside a firing combustion chamber. Like, we need to separate normal noise from a destructive feedback loop.
Well, and you have to realize the baseline environment of any rocket engine is incredibly chaotic to begin with.
It's not a smooth burn.
No, not at all. Normal combustion is never completely smooth. You've got liquid propellants atomizing, mixing, burning at literally thousands of degrees.
Right.
And that inherently creates turbulence. It creates pressure fluctuations.
So the way I picture it, it's like being in a crowded, echoing room.
Okay.
Like, you have 100 people. They're all having separate animated conversations. They're shifting their weight, moving around. It's loud, it's chaotic, but it's just harmless background chatter.
Right.
The floor isn't going to collapse under the weight of people moving randomly.
Right, because the energy is scattered.
But combustion instability would be like if that entire crowd suddenly synchronized their movements and they just started stomping their feet in perfect rhythmic unison.
Yes, that's a great analogy.
And suddenly the floor shatters.
Because when a crowd shifts around randomly, like you said, the total effect of those random fluctuations over time basically cancels itself out.
The room stays intact.
Exactly. But in combustion instability, the energy stops being random. It becomes highly periodic. It concentrates at specific inherent frequencies of the combustion chamber itself.
So the energy from the combustion process starts feeding directly into the acoustic waves of the chamber.
Right. It starts feeding the stomping. And when that happens, the pressure amplitude swings can exceed 5% of the average chamber pressure. And sometimes, they spike up to tens of percent.
Wait, tens of percent?
Yeah. And if you consider that the baseline pressure in a modern rocket engine can be hundreds of atmospheres, a rhythmic 20% swing is catastrophic.
You just tear the metal apart.
Exactly. It causes massive mechanical vibration that can snap pipes, and it severely spikes the heat transfer to the engine walls. It can physically destroy or literally melt engine components in the blink of an eye.
So for anyone listening, distinguishing between, harmless random system noise and a system-destroying feedback loop, that is a universal engineering challenge.
It's absolutely universal.
So we know what the beast looks like. Now we need to understand how it actually behaves. The physics of this chaos are categorized chronologically by frequency.
Low, medium, and high.
And it all depends on which parts of the rocket are essentially talking to each other in that destructive loop. So let's start with the low end. This is anything below 200 hertz.
Right. So low-frequency combustion instability is fundamentally a coupling between the combustion process in the chamber and the flow process in the propellant supply system.
So like the pipes, the valves, the pumps leading into the engine.
Exactly. And because the frequency is so low, the wavelength of the oscillation is much larger than the physical dimensions of the combustion chamber itself.
So the chamber itself isn't echoing. The whole volume of gas inside it is acting as a single unit.
Yes. It acts like a Helmholtz resonator. The entire mass of gas inside the chamber oscillates together, essentially moving like a single solid block of pressure.
Oh, wow.
Yeah, it's what we call a bulk mode.
Like a giant invisible piston slamming back and forth inside the engine.
That's exactly it. And that massive slamming feeds back up into the supply lines. It physically alters the flow rate and the mixing ratio of the propellants as they enter the chamber.
Which then creates another pressure pulse, keeping the whole cycle going.
Right. It can break propellant pipes, snap mechanical joints, and cause the engine's thrust to just severely fluctuate.
Unbelievable. Okay, then we move up the spectrum to medium frequency, which sits between, what, 200 and 1,000 hertz?
Yeah, 200 to 1,000. And this one is kind of the weird middle child. It mixes the feed system fluctuations with the actual chamber acoustics.
And the text notes this is especially common in variable thrust engines, which, if I think about how throttling works, you are continuously changing the flow rates and chamber pressures. That must change the acoustic properties of the chamber as well, right?
It changes everything. As you throttle a variable thrust engine up or down, you are actively changing the density and the temperature of the gas inside the chamber.
Right.
And that directly alters the speed of sound within the gas, which in turn shifts the resonant frequencies of the chamber.
So somewhere in that continuous adjustment of throttling, you are highly likely to hit a sweet spot.
Exactly. A spot where the shifting acoustics of the chamber perfectly align with the fluctuation in the supply system.
You essentially tune the engine into its own destruction radio station.
That's a fun way to put it, yeah.
But the absolute worst of the bunch, I mean, the one that keeps aerospace engineers up at night, is high frequency.
Oh, yeah. Anything over 1,000 hertz.
Because this is where the combustion couples directly with the acoustic resonance of the chamber itself.
Right. And what's fascinating here is how these high-frequency waves physically manifest. Because the geometry of a cylindrical rocket chamber supports different modes of acoustic waves.
Okay.
You have longitudinal waves, which basically bounce end-to-end from the injector face down to the nozzle. And then you have transverse waves, which travel perpendicular to the main flow of thrust.
Okay, so side to side.
Basically.
Right.
And these transverse waves come in two main types. You've got radial waves, bouncing from the center axis out to the walls, and then you have tangential waves.
Okay, let's focus on that tangential wave, because this is where the physical reality gets truly terrifying.
It does.
A tangential wave isn't bouncing end to end or center to wall. It's traveling around the circumference of the chamber.
Yeah.
It's essentially an acoustic tornado spinning along the inner walls.
Mm-hmm.
And the result is that it can destroy the protective boundary layer of gas near the walls and melt the engine's injector head in under 1 second.
Yep.
Wait, really? Is it the physical spinning motion of the wave that's scrubbing that layer away?
Yes. It acts almost like a supersonic squeegee.
A supersonic squeegee.
Yeah. Because rocket engines burn incredibly hot, right? Often far hotter than the melting point of the metal alloys they're constructed from.
Right. Which always sounds impossible.
The engine only survives normal operation because engineers carefully design a thin, cooler boundary layer of gas that hugs the inside walls. It acts as an insulating shield.
Okay.
But when a tangential transverse wave starts spinning, the sheer velocity of that pressure wave physically strips away that protective boundary layer.
It just wipes the shield right off the metal.
Exactly. And without that insulation, the raw, thousands of degrees heat of the core combustion violently transfers directly to the metal chamber wall and the injector face. And because the wave is spinning so fast, the convective heat transfer rate just spikes exponentially.
Wow.
That is how you go from a functioning, structurally sound engine to a literally melted puddle of slag in less than a second.
Less than 1 second. Which, begs the obvious engineering question. Since a high-frequency tangential wave can melt your engine before you even have time to blink, how do you build a rocket that survives it?
Well, you have to build physical hardware solutions to tame it.
Right. And the source document mentions 3 primary countermeasures to disrupt these acoustic modes. You've got injector face baffles, acoustic dampers, and injector modifications.
Let's look at baffles first. Engineers install physical dividers. They're called he in the Chinese literature, right on the injector face.
Okay.
This splits the head of the circular combustion chamber into smaller pie slices or grid sections.
So if the problem is a continuous circular wave, the most obvious solution is just putting massive physical roadblocks in its way, like dropping giant concrete breakwaters into a circular wave pool. The wave hits the wall, breaks apart, and just can't complete the circle to get that continuous rhythm going.
That physical blockage is a big part of it, yeah. But the more important mechanism is actually acoustic.
Oh.
By putting up those physical walls, you fundamentally change the acoustic geometry of the chamber head. You divide a large cavity into several smaller cavities.
And that matters because?
Because it significantly raises the natural frequency of those transverse waves. A higher frequency requires vastly more energy to excite and sustain. Plus, the edges of the baffles create vortices and friction that dissipate whatever acoustic energy does manage to build up.
That's so clever. But,
Yeah.
I mean, you can't just fill the entire engine head with massive metal dividers, right? The engine would be incredibly heavy, and all those complex welded corners would be super prone to thermal cracking under the extreme heat.
Exactly. Which is why baffles are usually limited to suppressing the lower mode transverse waves. For the really high frequency stuff, you turn to acoustic dampers.
Ah, specifically the quarter wave cavities.
Yes.
I love these. These are tiny tuned acoustic resonators. You essentially drill a series of small specific cavities into the walls near the antinodes of the waves, right?
Yep.
The spots where the wave's pressure amplitude is at its peak.
Right. They function on the principle of a Helmholtz resonator or a tuned pipe. You engineer the depth of the cavity to be exactly 1/4 of the wavelength of the acoustic frequency you want to kill.
Okay.
When the high-pressure part of the wave hits the cavity, the pressure travels down to the bottom, bounces off the back wall, and travels back up.
And because of that quarter wave depth, by the time the bounce wave reaches the opening again, it is exactly out of phase with the incoming wave in the chamber.
Exactly.
It uses the wave's own energy to cancel itself out. That is absolutely brilliant.
It really is. So for a large engine, you use a combination approach.
Right.
You put a few sturdy baffles on the injector face to kill the big low-mode transverse waves, and you line the walls with hundreds of these tiny quarter-wave cavities to eat up the high-frequency waves.
It's this elegant, multi-layered compromise between structural integrity and acoustic damping.
Yeah. And then the third method is tweaking the injector itself. You change the hole sizes, the angles, or the fuel distribution patterns to intentionally misalign the combustion energy release from the areas where the acoustic resonance is strongest.
So you move the fire away from the acoustic antinodes.
You don't feed the monster where it's hungriest.
I love that. Okay, so you've built your engine, you've installed your baffles, tuned your quarter wave cavities, tweaked your injectors. How do you know it actually works?
Well, you have to test it.
Because you absolutely cannot just bolt it to a launch vehicle and hope for the best in space.
Definitely not. You test it extensively, and one approach they used to use a lot is the hot fire statistical method.
Okay, what's up?
You just put the engine on a test stand and fire it over and over again, observing if it spontaneously develops instability during normal operation.
But, I mean, if I fire an engine 100 times and it doesn't blow up, that just tells me it didn't blow up yet. It doesn't actually tell me what my margin of safety is. I could be miles away from the cliff edge, or I could be balancing on a tightrope with zero room for error.
And that is the fundamental flaw of relying purely on statistical hot fires. The text explicitly points this out. It tells you nothing about the engine's anti-interference ability.
Okay.
To find that true margin of safety, aerospace engineers use the pulse excitation method.
Okay, here's where it gets really interesting. To test a liquid rocket engine, engineers literally fire pulse guns, explosive charges, or high-pressure gas pulsers directly into the firing combustion chamber.
Yep.
They deliberately shoot small bombs into the wave antinodes of an engine running at full throttle.
It seems totally counterintuitive, right?
Yeah.
To detonate explosives inside a machine, you are actively trying to keep stable.
It sounds insane.
But it is the absolute gold standard for testing. It evaluates a concept known as dynamic stability.
Meaning the system's ability to take a punch and keep standing.
Exactly, because spaceflight is an inherently violent environment. Disturbances are guaranteed. You might have a rough valve transition, a piece of slag passing through the injector, or a sudden aerodynamic shock.
Right.
The goal isn't to build an engine that theoretically never experiences a disturbance. The goal is to build an engine that, when hit by a massive, unexpected, explosive shockwave, can actively damp the oscillation and return to normal, stable combustion in less than 40 milliseconds.
40 milliseconds. That's practically a rounding error in human perception, but I imagine in acoustic cycles that's a significant amount of time.
It is enough time for the wave to bounce several times. If the engine's baffles and cavities can swallow the energy of an explosive charge and stabilize the combustion in under 40 milliseconds, it passes.
Wow.
Empirical practice proves that if it can survive that forced interference on the test stand, it will survive whatever random anomalies occur during actual flight.
So you don't hope for a calm environment. You engineer for rapid, aggressive recovery. I think that's incredible. Okay, so we've looked at the physical hardware, the baffles, and the explosive testing. Now I want to zoom way in, down to the microscopic mathematical level to understand the actual root cause of this whole phenomenon. Because, all these physical fixes are just treating the symptoms. To understand the disease, we have to look at time lag theory.
Right. At a fundamental physical level, combustion instability is a problem of time. Specifically, the combustion time lag, represented by the Greek letter tau.
Tau. Okay.
This is the finite time interval between the exact moment a drop of liquid propellant is injected into the chamber and the moment it completely reacts to become final combustion gas products.
Because even in a raging inferno, physics takes time.
Exactly. And the time lag is divided into two distinct parts. First is the invariable lag.
Which is what...
This is the physical time required for the liquid streams to break apart into droplets, atomize, evaporate, and mix. It's largely a mechanical process and doesn't change much based on fluctuations in chamber pressure.
Okay, got it.
Second is the sensitive lag. This is the time required for the actual chemical reactions to occur. And this portion is highly sensitive to the pressure and temperature inside the chamber.
Wait, if the chemical reaction time changes based on pressure, how does that actually create a destructive vibration? It has to sync up with the acoustic waves we were talking about earlier, right?
Yes, and this is governed by something called Rayleigh's criterion. Lord Rayleigh discovered that if you add heat to an oscillating mass of gas at the exact moment its pressure is highest, you amplify the oscillation.
Okay.
If you add heat when the pressure is lowest, you damp the oscillation.
So it's like pushing someone on a swing.
Exactly like that.
If you push them exactly as they reach the highest point of their arc, they go higher. If you push them at the wrong time, you kill their momentum.
That is exactly the mechanism. Now imagine a random pressure wave passing through the chamber. The pressure goes up slightly. Because the pressure is higher, the sensitive time lag decreases. The chemical reactions suddenly happen faster.
Right.
But there is a delay. That total time lag, tau, before that freshly injected fuel actually burns and releases its energy.
And if that time lag tau happens to perfectly match the time it takes for the acoustic pressure wave to bounce back and hit its peak again,
then that massive burst of chemical energy is released at the exact highest pressure point of the acoustic cycle. Rayleigh's criterion is fulfilled.
what?
The wave is amplified. This draws in more propellant, which burns faster, releasing an even larger burst of energy at the next peak. The cycle just rapidly spirals out of control.
Okay, let me challenge this with a hypothetical.
Sure.
Let's say I'm the greatest aerospace engineer in history. I build a perfect feed system. The pipes are infinitely rigid. The turbopumps have zero fluctuation. The flow is mathematically flawless.
Okay.
The liquid enters the chamber perfectly smooth. Can the engine still become unstable?
Yes.
Really?
Yes, and this is a chilling reality for propulsion engineers, known as intrinsic instability. Even with hardware that is 100% mechanically perfect, the physics of the combustion itself can cause destructive oscillations.
How is that possible?
It all hinges on a mathematical variable called the pressure interaction index, denoted by the letter N.
What does it represent?
It measures how intensely the chemical reaction rate reacts to a change in pressure. It is a sensitivity dial. The mathematical models dictate that if N is greater than 0.5, the increase in the rate of energy release will mathematically outpace the natural acoustic damping of the chamber.
So if N is greater than 0.5, the sheer pressure sensitivity of the sensitive time lag will cause the system to spontaneously shake itself apart.
Yes.
No matter how perfectly the hardware was machined.
Exactly. The sensitivity outpaces the damping, creating a runaway positive feedback loop from within the chemical reaction itself. The math guarantees instability.
That is a staggering realization and really applies to any system you interact with, like markets, traffic, workflows. Delays between an input and an output, combined with high sensitivity to pressure, will inherently create chaotic oscillations.
It's a universal principle of dynamic systems, yeah.
So what does this all mean? We've covered an immense amount of ground today. We started by exploring the terrifying reality of a tangential transverse wave that can spin around a chamber and melt an injector head in under 1 second.
Yeah.
By stripping away its boundary layer. We looked at how engineers fight back by installing structural baffles and tuning quarter-wave acoustic cavities to cancel out specific frequencies.
Right.
We learned that to test these massive machines, engineers deliberately shoot explosives into the antinodes, demanding that the system damp the shock wave in 40 milliseconds.
40 milliseconds.
And finally, we zoomed into the math of time lag theory and Rayleigh's criterion, realizing that if the pressure interaction index crosses that 0.5 threshold, the chemistry itself guarantees destruction.
Mastering those variables is basically the great triumph of modern propulsion engineering. But there is one final detail regarding how we model these systems today that I think provides a pretty sobering perspective on all the technology we build.
Oh, Lay it on me.
So, toward the end of the technical documentation, it discusses numerical integration methods.
Okay.
This is how modern computers model the chaotic fluid dynamics inside the chamber, calculating the state of the gas step by step, grid by grid. Older linear mathematical models assume that instability worked on a slope.
Like a gradual thing.
Right. If a system was inherently unstable, even a microscopic disturbance would gradually grow until it destroyed the engine.
But nonlinear numerical integration shows something different.
It shows something vastly more complex. By accounting for the chaotic, nonlinear feedback loops of fluid dynamics, these modern models reveal that an engine can be perfectly dynamically stable against small, everyday bumps. The acoustics stamp out, the time lags don't align, it hums along beautifully. But if a disturbance comes along that crosses a specific, finite threshold of energy, the nonlinear math shows the entire system doesn't just degrade smoothly.
What?
It instantly crashes into violent, unrecoverable instability.
So it's not a slope, it's a structural cliff.
A cliff that is entirely invisible until you fall off it. So I'd leave you with this thought to mull over. The most advanced, meticulously engineered machines humanity has ever created are operating in a mathematically chaotic regime.
Right.
We can never theoretically prove they are absolutely stable under all conditions. We can only prove, through explosive testing and rigorous modeling, that their threshold for destruction is just slightly higher than the chaos we expect them to encounter. So look at the complex systems in your own life, your business, your community. Are they truly stable? Or are they just waiting for a disturbance large enough to cross their hidden threshold?